second semester, however, when we start talking about electric circuits. However, you get introduced to it. Now, if you recall, I left off last time in class by beginning to introduce the following problem. We're going to calculate the size of the event horizon, also known as the Schwarzschild radius, named after the physicist who first described it, associated with black hole. We're going to arrive at a general expression for this radius. It's such a famous equation it actually appears on t-shirts every now and then. And then we'll calculate what it's equal to for a couple of different types of black holes of different masses. Now remember our setup from last time. Essentially think of a black hole as two things. You first of all have literally a point in space. It's zero size of finite mass, but of then therefore infinite density. Then you have some distance away from that point. The point, remember, is referred to as you have some distance away from that point, equivalently called the event horizon or Schwarzschild radius, where it literally is a horizon. It's a point beyond which you can't see. So if you were standing away from the black hole in some manner and looked at it, you would see a perfectly featureless black sphere, but you're not looking at a structure. You're literally looking at a horizon. The reason for this is because you can't get any information from material that may be, say, right here, in between this distance and the actual singularity itself. The reason for that is because in order for that information to reach you, it would literally have to have an escape velocity that is greater than the speed of light. So then therefore, this point right here is a point beyond which you can't see. What we want to calculate is that distance to that point is from the singularity itself. This is the Schwarzschild radius. This is the radius of the event horizon. Yes,
so something could potentially escape from that, but you wouldn't be able to see it.
No, because you would literally have that object fall back in. It could be impossible for it to escape. It would literally have to have a speed greater than that of light in order to do so. So regardless, in other words, if you're closer to the singularity than the event horizon is, you're not coming back.
Yeah,
you're going down the drain.
How is it possible for there to be mass that occupies no space?
How is it possible for there to be mass that occupies no space? I'll give you a basic understanding of this in just a few minutes. Let me run through the calculation itself, which is actually quite easy. Okay, now what we do is we set up an escape velocity calculation where the escape velocity itself is equal to the speed of light c. The speed of light c is one of nature's fundamental constants. The speed of light c is 3 times 10 to the 8th meters per second. This is the speed of light. 300,000 kilometers per second, about 186,000 miles per second. The distance that light travels in 1 year, by the way, based upon the speed, is about 6 trillion miles. Okay, then, with our escape velocity calculation that I performed at the end of class last time, remember then that you have mathematically an object which ends up an infinite distance away from, in this case, the singularity, with a speed of 0. Okay, now the black hole itself literally occupies 0 size, but it does have a finite mass. So there's a mass associated with the black hole itself. Let's just call that m hole. Okay, now what we do, as I said, is set up an escape velocity calculation, very similar to what you saw me do at the end of class last time with conservation of energy. So we set up our conservation of energy situation. First of all, we have change in kinetic energy. Final kinetic energy of the object is 0, and then the rest is far away. Now watch this. The initial kinetic energy is going to be the following. Oh, there it is. A little bit of MC squared. Okay, then we add to that the change in gravitational potential energy. Remember, it's Newtonian sense that gravitational potential energy in general is equal to the following expression. And therefore, our final gravitational potential energy is 0 because the object ends up infinitely far away. And minus the initial, which is not 0, where our choice of origin here is the black hole itself. Our initial gravitational potential energy depends upon this distance r away. Once again, this is our unknown calculation. So final minus initial. So, okay, now if I just cancel out some negative signs here, like so, and then move this 1/2 mc squared to the other side, following expression, and notice that the mass of the object itself, m, cancels for the expression. So, and then if you just cross multiply it a little bit and then solve for capital R, this is what's known as the distance that the event horizon is from the singularity, you end up with the following expression, which is so famous that you actually, in fact, do see it sometimes on t-shirts. So, and now what I want to do is for a couple of different sized black holes is calculate what the Schwarzschild radius would be. So for example, imagine taking the Earth and squeezing it in some manner. You squeeze it in some manner such that eventually you get to a certain point where gravity becomes literally unstoppable. The object undergoes what is sometimes called a final gravitational collapse. It literally collapses to a point. So if you could turn the Earth itself into a black hole, how big would the event horizon be? Imagine looking at the Earth as a black hole. How big would that perfectly featureless black sphere be? Well, in that particular case, what we would do is we would set the mass of the black hole here equals the mass of the Earth, which is 6 times 10 to the 24 kilograms. So then therefore, the Schwarzschild radius, capital R, would be equal to the following distance in terms of meters. So in terms of meters, we would now have the following. All 2 times 6.67 times 10 to the minus 11 for capital G, that's a given. Multiplied now by the mass of the black hole, which is the mass of the Earth in this case, 6 times 10 to the 24, and then divided by c squared. C up on the top board is 3 times 10 to the 8 meters per second. When you square it, it's 9 times 10 to the 16th. So plugging that in appropriately gives me the following distance in terms of meters. It's 0.009 meters. That's 9 millimeters. It's about a centimeter. So if you could somehow turn the Earth itself into a black hole, the Schwarzschild radius, the diameter of it, about 2 centimeters, be about that big. So imagine looking at a perfectly featureless black sphere this big somewhere in this room. By the way, if a black hole with the mass of the Earth was somewhere here in this room, we would have some really serious problems. But imagine that object was there, and it's like sitting there in the middle of the room, and you would be so tempted to just kind of reach your hand down and grab it. Well, if you put your hand in, you're not getting your hand back. You're going all the way down the drain. It's going to drain you over the drain. Okay, now let's calculate the actual size of a known black hole. Let's do so for the black hole that's at the center of the Milky Way galaxy. Remember back in chapter 6 that we briefly examined that as a problem. So now in the second calculation that I'll do here, let's say that it was the mass of the black hole is equal to 4.5 million solar masses. So that would be 4.5 times 10 to the 6, that's 4.5 million, multiplied by then the mass of the sun, which is about 2 times 10 to the 30th kilograms. So this right here is the mass of that black hole in terms of kilograms. Let's plug it into the expression here for the Schwarzschild radius and calculate how big that is. Once again, this is for a real black hole, the one that's at the center of the Milky Way galaxy. How big would that marble, if you will, be? 2 times G, I'll keep the numbers here appropriately. So, times the mass of this black hole, which is 4.5 million first, multiplied by 2 times 10 to the 30 kilograms for the mass of the sun, divided by c squared, once again, 9 times 10 to the 16th. In terms of meters, it's certainly a lot bigger than that. It's about 1.3 or so. Times 10 to the 10th meters. So now, how big is that? Well, let's compare it to an astronomical unit. This is actually smaller than an astronomical unit. The amount of AU that this is equal to the following. I'm going to convert this distance here in terms of meters into astronomical units, which is about 150 million kilometers, 1.5 times 10 to the 11 meters, by just dividing a little bit, like so, and it comes out to be about, it's about 1/10 of an AU. It's about 0.09 AU. The next generation of telescopes, which are currently starting to be built, one of the things that they will be designed to do is to look really clearly into the heart of the Milky Way galaxy and perhaps actually see this. This right here, this distance, about 1/10 of an AU, is about on the edge of what our current telescopes might be able to see, a distance of 30,000 light years from the Earth. The next generation of space telescopes should be able to see this. Now, how would we be able to see it if it's a perfectly featureless black sphere? Well, as stuff falls down the drain, it heats up. And when it heats up, it gives off light. So conceivably, as something is falling down the drain and we see light being emitted from that material, we think that we might be able to see the event horizon kind of like silhouetted, if you will, against some of that light as the material goes down the drain. So we literally hope to be able to take a picture of the dragon at the center of the Milky Way, maybe when the next generation of telescopes are completed in terms of their construction. Okay?
I remember you were talking about a black hole that's the center of the Andromeda galaxy. Is that right?
We think that there is a massive black hole, at least one at the center of all galaxies, whether or not they be spiral or elliptic.
No, it was at at a cluster, I believe.
Yeah, that one's a lot further away, however, M87, that particular galaxy is about 50 million light years from the Earth. Okay, the black hole that's there is absolutely gigantic, but simply it's too far away for us to be able to see it directly.
How close is that planet that whips around it?
How close is that star that
That's
whips
just a
around?
star? Okay.
That star, I believe, at closest approach is somewhere in the neighborhood of 120 AU from the black hole, which is 3 times the distance that Pluto is from the sun. There you go. Right now, they have literally started construction. The next generation of land-based telescopes will have primary mirrors that are 30 meters plus wide. It will be about 3 times wider than the current largest telescopes, which are in the 10-meter range. Land-based telescopes, the next generation of them, usually is based upon approximately a 25-year limit. So the last generation of telescopes that was built on the ground with mirrors that are 10 meters wide, construction on those telescopes started around 1990 or so, which was about 25 years ago. So the next generation of telescopes is literally starting to be built right now. Ground was actually broke only about 2 weeks ago for the University of California's 30-meter telescope, which is currently now being built at the summit of Mauna Kea in Hawaii. Summit of Mauna Kea in Hawaii is probably the best place in the world to do astronomical research. Now, Bailey asked me a few moments ago exactly how is it that you can have an object that's literally 0 size. Now, I've already given you a basic primer on what a black hole's creation comes from. Well, let me give you a little bit of further details. When very massive stars, remember, end their lives, they undergo these catastrophic explosions called supernova explosions. And as I previously have mentioned, all the material on the periodic table past iron is synthesized in such an explosion. However, when this process of the supernova explosion is occurring, all of the infalling material of the star takes the core of the star and it crushes it. Now, if the star is not very massive, like in the case of the sun, for example, basically what the collapse of the star will do is it will arrange all of the electrons associated with atoms into their tightest possible configuration. This is a state that is referred to as quantum degeneracy. When this occurs in a low-mass star, the object that is left over in this state is called a white dwarf. However, in a medium-mass star, as the star undergoes the collapse, basically what literally happens is that gravity is so strong that it will actually cram the electrons into the protons themselves, thereby creating neutrons. And so what you eventually end up with then is a gigantic ball of neutrons, what is referred to as a neutron star. But if the star is more massive still, gravity ultimately wins the game. Not even the strong nuclear force of those really tightly packed neutrons is enough to withstand the final gravitational collapse. And then literally, the object collapses down to a point. That's what a black hole is. It's born in the supernova explosions of extremely massive stars. So then what would actually happen to you if you fell down the drain? Let's say you got closer to the singularity than the event horizon itself. What eventually happens as you fall down the drain? Well, imagine it like this. Let's say that you fall feet first into the black hole. As you fall further and further down the drain, the space around the black hole becomes increasingly warped. What this means is that eventually you're actually going to feel a difference in the amount of gravitational pull exerted on your feet as opposed to your head, because your feet are closer to the singularity, you'll actually experience more gravitational force on your feet than you would on your head. And so then therefore, what will literally begin to happen is that your body starts to get stretched lengthwise like so as you fall into the black hole. This is a process, by the way, that is referred to as spaghettification. So eventually then what will literally happen is that your body will be torn apart, eventually into its constituent atoms. And then imagine the atoms as they fall further and further down the drain. The same thing happens to the atoms. The difference in gravity exerted on the top portion of the atom is different than that on the bottom portion of the atom as it falls downwards like so. That difference becomes so great, it's referred to as a tidal force, by the way, that eventually the atom gets torn apart into its constituent subatomic particles. And then the same thing happens to the subatomic particles as they go down the drain. The protons, for example, get torn up into their constituents, which are referred to as quarks. And then what happens after that is the quarks fall further down the drain. We literally don't know, because that's actually where our knowledge of physics ends. Where physics is today actually cannot explain physically what happens, if you will, at the bottom of the drain, at the bottom of the well, at the singularity itself. We don't, as of yet today, have the physics to understand that. Why that is, it's a very long story that I will get to in brief when we do eventually get to chapter 9. Oh, last question, and I need to move on.
So electrons don't have volume either, do they?
Maybe,
Maybe.
maybe not.
So, but
Once
maybe,
again,
Hold up.
that's a really long
I'm not-
story,
I don't want
which
you-
I will
I don't want you to
briefly
start.
address when we eventually get to chapter 9.
Okay, hold on then. That's not what I'm asking about.
The original equation that you wrote for the change in gravitational energy, it's zero minus, it's
So
final minus.
final minus initial. The final gravitational potential energy is 0 because your distance r is infinity. So remember that the expression is up there at the top of the board. When r is equal to infinity, when you're infinitely far away from singularity, then the potential energy is 0.
Zero, okay. What about the second part?
Guys in the back, please quiet down. Guys in the back, please quiet down.
Why is the initial that equation?
So the initial, remember, is not 0 because our choice of origin is not the surface of the Earth, or in this case the event horizon, but is instead the center of the diagram, in this case the singularity, or as I originally defined it last time in class, in terms of the center of the Earth. So we define things in this manner essentially because potential energy ends up being a -1/distance calculation. So that's why things are defined as they are.
So we are, the initial plate, the final destination, the initial point that we start is the singularity.
No, the initial point is some distance away from the singularity, in this case the event horizon itself.
Okay.
So you're never at the singularity in this calculation.
Okay. You can,
All right, moving on from there. Let me complete one more problem here in this section of Newtonian gravitation prior to beginning to move on to our last topics. Once again, we'll kind of move back towards the Earth in doing this. Let's see exactly how much energy is necessary to launch a satellite into orbit. Now back in chapter 6, when I talked briefly about the space elevator, I mentioned that it's prohibitively expensive to get up off the Earth and launch something into orbit. In this case, we'll say at a circular orbit, 500 kilometers above the surface of the Earth. And what we're going to do is place a reasonably sized payload, as it's called, into low Earth orbit in this manner, a payload that has a mass of 100 kilograms. So it's like, something probably smaller than a DESC, frankly. Watch how much energy is necessary to do this. Once again, for simplicity, we'll ignore the Earth's rotation. Now, unlike the previous problems that I've done here with regards to Newtonian gravitation, potential energy in this form, in this example, we're going to have a non-conservative force present. what we'll do is we'll picture our satellite starting at rest on the surface of the Earth. So it says ignore the Earth's rotation. And then what we'll do is we'll think of the engine as a pushing force. What we're going to do is push the object up into low Earth orbit. And we're going to calculate the work done by that pushing force. That's the amount of energy that's necessary to launch the satellite into orbit. So this is a non-conservative force problem. So picture the problem and therefore like this. Here's the Earth-like zone. Here's the mass of the Earth m sub e. And then we just start right here on the surface of the Earth initially at rest. Once again, we're ignoring the Earth's rotation here. So, and then what we do is we just push the object up to low Earth orbit, say, like so, and then just at the right moment, like so, we shut off our engine. And when we shut off our engine right here at this moment, our satellite has a speed v such that it does end up in uniform circular motion. So, think of the pushing force that gets us up there with that speed. Think of that as a non-conservative force. This is the work that is done by the engine. That's what we want to calculate. The work done by the engine, which is then therefore equal to the energy necessary to do this. Okay, now once we understand that, calculating this out is actually fairly straightforward. So what we have first of all is our object of mass m, that's given to us as 100 kilograms. We have some known quantities here. Of course, we have capital G once again. I'll rewrite it. So, we have the mass of the Earth. Like so. Because remember that our origin is the center of the Earth, our initial position here is equal to the radius of the Earth. So right here is the radius of the Earth, r sub e. That, of course, is given as well. The radius of the Earth, r sub e, is 6.4 times 10 to the 6 meters. And then we have one more known number here in this problem, and that's the radius of our circular orbit like so when we shut off our engine. We're given that that distance is 500 kilometers above the ground. So then therefore the distance small r here on my diagram is 6,400 kilometers for the radius of the Earth, plus the additional 500 for 6,900 kilometers. Small r, 6.9, 6 meters. Okay, now we set up the problem in the following way. I said, think of the work being done by the engine here as a non-conservative force. So then therefore, we have the work done by that non-conservative force, by the engine, then resulting in the change in the kinetic energy plus the change in potential energy of the satellite itself. Now all that we have to do is fill in all of these terms. So first of all, the change in kinetic energy. We have a final speed v. We don't know what it is as of yet, by the way. We will be able to calculate in a few moments. But for now, the final kinetic energy is 1/2 mv squared. The initial kinetic energy, if we ignore the Earth's rotation, is equal to 0. And then we have our change in gravitational potential energy. Final gravitational potential energy, that's upon the distance small r. So our final gravitational potential energy is equal to the following quantity, minus then the initial gravitational potential energy, which is not 0, remember, but instead is dependent upon the distance that we are from the center of the Earth to start with. That distance is equal to the radius. Now, does the mass of the satellite, 100 kilograms, cancel out here? No. This is not 0. This is something that we're trying to find. So basically, I just have to calculate out all of this stuff to get my answer. Now, how do I calculate all of that stuff if I don't know what the speed v is? But I do know how to calculate it, because it says that the satellite ends up in a circular orbit. So then, therefore, we can find the speed v, the orbital speed, if you will, by doing a little bit of F equals ma, like we did back in Chapter 6. Back in Chapter 6, for basic orbit problems, if you recall, we have the following. We have the force of gravity acting on our satellite, Gmm over r squared, equals then mass times acceleration, mv squared over r, where the v there is our orbital speed. So just using a little bit of F equals ma, we can figure out what the orbital speed v is, and then plug it into the expression. Frankly, algebraic, the easiest way to do this is actually take that expression and just solve it for mv squared, and then just stick it here. So I'm just going to cancel here an r from each sideways, so I'm not going to bother canceling mass because I need it here anyway. And now I'm going to take that expression for mv squared and just plug it right here. So let's now see what we begin to get as I calculate the work done by the engine. So I first of all have 1/2 mv squared, which is in there for this guy here. And now just watching our negative signs here carefully, I have minus GMM over little r. Like so. And then minus negative is a plus GMM over the radius of the curve. Like so. Because this is going to give my calculator a bit of a workout, you definitely want to simplify this as far as we possibly can. So I'm going to do two things here at once. First thing that I'm going to do is factor out the GMM from each term I only want to deal with at once. And then I have right here a 1/2 1 over r minus 1 over r. What is 1/2 1 over r minus 1 over r? Negative 1/2 over r. So therefore, you end up with the following expression. So the work done by the engine is first of all the constants here pulled out, G and M, and then I'm left with the following. 1/2 minus 1 is negative 1/2, 1 over little r, but I still have plus 1 over the radius of the earth. Now, do I expect to get here, by the way, a positive number or a negative number for the work done by this pushing force? Should be positive. Let's see what that is. I'm going to do the parentheses first. And first of all, I have negative 1/2, then multiplied by, or actually divided by little r, which was 6.9 times 10 to the 6th. Okay, then plus 1 over the radius of the earth, which is 4 times 10 to the 6th. The parentheses is a positive number. Times g times the mass of the earth times the mass of our payload, which remember is given to us as 100 kilograms, so reasonably sized satellite. End up with a gigantic number in terms of joules. 1, 2, 3, 4, 5, 6, 7, 8, 9. About 3.3 billion joules. 3 times 10 to the 9 joules. And as you can see from a calculation such as this, it's prohibitively expensive to get up off the earth. This is the hard part. Once you get up off the earth, however, going anywhere else in the solar system is actually relatively easy to do, once again based upon work energy calculations such as this. Okay? Okay?
How much fuel is that?
Well, it depends on what your bang for your buck is. How much potential energy you have associated with the fuel, how many joules of energy per kilogram of fuel you have. So you want to try to use, obviously, the most efficient fuels that you possibly can. All right, moving on from there. Our next topic here in Chapter 8, which, yes, for honors kids last year, you didn't see, is actually a brief look at a tool that is sometimes used in physics to very quickly and sometimes even just qualitatively evaluate what can happen in a physical situation. We do so with a specific type of diagram. It's called a potential energy diagram. Perfect example to begin examining what is called the potential energy diagram is actually a roller coaster. A roller coaster by itself is actually a potential energy diagram. Now here's what I mean. Let's say that our roller coaster consists of a couple of units. Okay, now at any one moment, of course, the potential energy would just be equal to mgh, where h is the height of the track at some moment in time, at some point here along the roller coaster itself. However, the height of the track also depends upon, by the way, where you are on the track. So let's consider this axis of a graph that I'm about to describe, diagram that I'm about to construct. Let's call this distance here horizontally direction r. This is typically, by the way, how it's described in this context for a potential energy diagram. What that means is that the potential energy itself, which is a function of the hill h, is also a function of r, because the height of the track at any point depends upon where you are. So this expression here is actually a function of this distance r where you are on the track, where the height h is then therefore a function of r. In other words, also height h is some value here, and value r is a different value of h here, and a different value of r, and so on and so on and so on. This equation that I just wrote down right here is describing the following potential energy diagram. On this diagram, vertical axis is the potential energy itself. It's the potential energy U. The horizontal axis is the distance r that you happen to be along the roller coaster track itself. So the roller coaster hills, if you just think of it as linear, being a line, is actually a diagram that describes potential energy. So this function here in green that I've just described is basically this expression. Now, how is a diagram such as this useful in describing very quickly what can possibly happen in a physical situation? Well, let's think of it like this. Let's say that we give our coaster track, or our coaster cart, excuse me, some set amount of energy. Let's just simply call that energy E. And let's happen to say that that energy E, which is a constant, is represented by this horizontal red line. Okay, now, if the energy is conserved, and it always is in situations, by the way, involving potential energy diagrams, so they're only useful when describing conservation of energy situations. This is in a very quick qualitative way. Let's describe what can happen. Well, for example, right here at this point when we are at the top of this first hill, what is the potential energy U itself in green equal to? It's equal to the total energy E. Now remember, the total energy E is kinetic plus potential. So then therefore, right there, what is the kinetic energy equal to? It's equal to 0. Okay, now let's say that we go from here to here. Right here at this point, what is the potential energy in green equal to? It's equal to 0. And then therefore, what is the total energy E equal to at this point? It's equal to the kinetic energy K. So notice that the kinetic energy K is actually just the difference on this graph between the constant energy E here in red and where the green line happens to be to describe the potential energy itself. So the kinetic energy K here is equal to the difference, E minus U. So now take a look at that difference at different points along the track. Right here, the difference is equal to 0. So if the difference here is equal to 0, then the kinetic energy is equal to 0. Right here, the difference itself is equal to E minus 0. It's equal to the total energy E. Therefore, the kinetic energy right here is equal to the total energy E. And then, where is the kinetic energy bigger? Here, here. Here it is. Because the difference here is larger, total minus a small potential energy equals large kinetic energy, like so. The difference here is a smaller number. Total energy E minus a bigger number for potential energy here equals a smaller value of kinetic energy. So very quickly on a graph such as this, you can understand, just in a qualitative way, the motion of the coaster cart itself as it moves along these hills. But now let me take the total energy E and change its value. Now, let me say that I give the coaster cart a total energy E that instead looks like this. So, let's say that I give it less energy. If I give it less energy, let's briefly examine, first of all, what happens right here. Now, what happens right here in terms of the energy? That is, what is the kinetic energy, K, equal to right here? It's equal to 0. The difference between the red, V, and the green, U, is equal to 0. The kinetic energy right there is equal to 0. All the energy is potential energy. Once again, however, what happens right here? In what form is all of the energy right here? It's all kinetic energy because the U in green is equal to 0, and then therefore E minus 0 is equal to kinetic energy K. Right here, all of the energy E is equal to kinetic energy. And then what happens right here once again? What's equal to 0? The kinetic energy K is equal to 0. What this means is that if I start the coaster right here with this amount of energy and let it go, it's confined to this well on this potential energy diagram. It can't make it over this hill. It can't make it over this hill. The reason why mathematically is simple from this diagram, think of it like this. If the object was right here, what type of number would the kinetic energy be? It would be negative. Because notice you would have total energy E as some number, minus potential energy U, which is a bigger number. A number minus a bigger number is negative. Can kinetic energy, 1/2 mv squared, ever be negative? No, it cannot. So then therefore you cannot make it over this hill. This region right here, as we say, is unallowed. So then therefore, if you set the object right here with this total energy E in red, and let it go, it is just going to oscillate back and forth like so in this well forever. These regions here are forbidden because we don't have enough energy to make it over this hill to get to the sun. Gabe?
Is this kind of like, isn't this kind of like the study that Galileo did with like dropping an object and then only
Yeah, a
goes
little
the same
bit.
height?
I mean, because what you could do is you can think of that well that I have there on the left-hand side of the diagram. It's a crayon. Consider it your following way. Let's take a look here, just still in a qualitative way, at a specific potential energy example. This is, of course, spring potential energy. What type of graph is associated with this potential energy diagram for spring potential energy? It's a graph. It looks like this. So then therefore, if I give the oscillator some energy, like so, it will oscillate from this point here, this value of x, to this point here, this value of x forever, and it will never be able to go to these other regions because it does not have enough energy to do so. Now, if you did this in terms of a pendulum, you would end up with exactly the same diagram. You would end up with the pendulum being confined between this point here and this point here on this potential energy diagram. Okay, now that's essentially the gist of it in a qualitative way as to very quickly how you can come up with a description of the allowed or unallowed motions, but there's also a little bit of math that goes into the basic use of this diagram as well. It's described in the following way. What we do is we start with the work done by the conservative force. Work done by the conservative force, just in general, is equal to the following integral. What I want to do is relate this basic expression to either of these graphs, just in general, in terms of the variable r. How do I go about doing that? What we do is we take, first of all, the work done by the conservative force and make it negative to get the work done against the conservative force. Let's look back at how to stop talking. Okay, now, when you are introduced to potential energy diagrams, as we're doing here in Chapter 8, we only deal with one-dimensional cases. So I'm just immediately going to drop the dot product here and write this quantity in font. one-dimensional cases, the expression just looks like this. Okay, now remember that the work done against a conservative force is equal to the change in potential energy between these points. Now here's how I go directly from this statement here to the graph above. What I take a look at is just the infinitesimal displacement. The infinitesimal displacement then, when the object is moved over it, results in an infinitesimal change in potential energy. So I'm going to drop the negative side instead of write it like this. Now why did I bother doing it? Well, watch the last step. Solve for the force. You end up with this expression here. How is that expression for the conservative force itself related to this diagram above? What is it describing? What does a derivative always describe on a graph?
Change in
Okay, but just graphically, what does the derivative always describe? It's the slope of a line tangent to the curve. So take a look at it now in the following context. Let's say the object happens to be right here. Okay, now the tangent line itself would be the following slope. So, the slope of that line is the derivative at that point. How does the force itself act on it? It's the negative of that slope. Notice that the slope here that I drew in blue is a negative number. The force, however, is the negative of that. It's positive. So then therefore the conservative force acting on the roller coaster cart will cause the coaster cart to move in which direction, right or left, on my diagram, to the right-hand side. Once again, the tangent line itself has a negative slope. The force in terms of the distance r is the negative of that. The negative of a negative is a positive, therefore the conservative force will act such that it pushes the object in this direction. Same thing on the other side. If you look right over here on the other side, the tangent line right there, the slope of it is a positive number. So then therefore the conservative force will act such that it causes the object to be forced in the opposite direction, like so. So on a potential energy diagram, the conservative force is related to the diagram itself in the following manner through the mathematics here that I described. Now with respect to this topic, we're just getting a taste of it here, really not much else. Let's just take a look at it for a couple of examples. Let's do a little bit of PChem. You guys know what PChem is? PChem is physical chemistry. This is the potential energy function associated with a diatomic molecule, something that is bonded in a covalent bond. The covalent bond itself, as you'll see in part, can be modeled as a spring. You'll see why as we actually draw out the potential energy diagram associated with this function. Now, in order to draw out this potential energy diagram, we're going to break it up into some pieces. Now the A and the B there are constants. They're dependent upon the actual atoms that make up the molecule. values are really important for our analysis. Just to give you a basic idea of how this should work. And what we're going to do here in pieces is construct a potential energy diagram associated with, yes, admittedly, this rather complicated function. What we're trying to come up with here ultimately is a description of the following graph. And then once we have it graphed out, we'll do this as a series of steps. Then we'll understand the different types of motions that could occur with these atoms within this diatomic molecule. So yeah, we're doing a little bit of physical chemistry. Okay, the first part of the problem is to figure out at what value of R, so, is the potential energy equal to 0. In other words, somewhere on this diagram, my potential energy function is going to cross this axis in some way. We want to figure out where that is. Well, easy enough. All that we have to do is part of the problem, we set the potential energy here equal to 0, like so. And then yes, in terms of A and B, we'll just go ahead and solve for R. Thank you. So the first thing I'll do is I'll move the negative term over here to the left-hand side. Just like this. And I'll do a little bit of canceling out as well. If you cancel out an R to the 6 from both sides of the expression, what do you end up with on the right-hand side? You have R to the 6. So, then the last step here is just to cross multiply a little bit, and then I'll take a 1/6 root. So when I do this process, I end up with small r being equal to the following number, whatever it happens to be. So, now technically, yes, it's plus and minus, but in this particular problem, we're just going to work on the right-hand side of the diagram, as I've already begun to describe it. So this right here, this value of r, somewhere over here, that's where our potential energy function is going to cross the axis. Now, let's see. So now we want to describe the potential energy as R approaches 0. What the heck does R approaching 0 mean? Well, it means taking this diatomic molecule, where the covalent bond is bonded against this spring, and now we start to make the distance R small, start to bring these guys together. What happens to our potential energy as we do? Well, just take a look at the function itself up here on the top board of the screen. Imagine making R smaller and smaller and smaller. What happens to the potential energy U? It gets bigger and bigger and bigger. Now, which term? Negative term? Positive term gets bigger faster as R gets smaller and smaller. Again, the positive term gets bigger faster than the negative term does. This is an R to the 12th down here as opposed to an R to the 6th. So then therefore, if you set R equal to 0 and then therefore end up with infinity, is it positive infinity or negative? It's positive infinity. So this then tells us immediately that our potential energy function is going to start up here like so at positive infinity when R is equal to 0, and will then cross the axis like so at this particular point. So that's part B of the problem, understanding that our potential energy blows up to positive infinity when R is equal to 0. Okay, now part C of the problem works much the same way. Now what we want to do is we want to make R equal to infinity. If I make R equal to infinity, what then happens to the potential energy U? It becomes 0. What does the potential energy when R is equal to infinity approach 0? From the negative side, positive side. Approaches it from the negative side. The reason we know that is because my potential energy function is across the axis. So then somehow what my potential energy function has to do is start up here at infinity, cross the axis, and then somehow do this. Approach 0 when R is infinitely large from the negative side. So just from parts A, B, and C, start to begin to see what the function itself looks like. Yes.
How do you know it doesn't just come down and touch the axis and come back up?
How do I know it doesn't come like this?
No, like touch the axis.
Touch the axis and what, I'm sorry?
And not cross.
Like bounce one.
Just touch it. Go back up.
Oh, you mean come down like this and then come back up?
Yeah.
Okay, you can also think of it this way. As R approaches infinity, which of these guys gets smaller faster? This does. So in other words, you have a negative number here that's bigger than a positive number as R gets bigger. So then therefore you have to approach zero from the negative side. And the next piece of the process, this is really the last step. This part's now a D.
For part C, how do you know it's definitely approaching zero?
Okay, well, if R becomes infinite, then each of these terms are zero. Which one becomes zero faster? This one does. Therefore, this is still a finite number. It's negative, and this one is already zero. Therefore, we have to approach from the negative side. Okay, the next step in the process is part D. Where's the derivative equal to zero? What am I calculating when I do part D of the problem? The location of what? A tangent line being equal to zero means we're calculating a maximum or a minimum. Specifically, which one is it in this context? If somehow this has to happen, it has to be a minimum. That's right. That's what we're finding here, which is a simple first derivative test in part D of the problem. So in part D of the problem, then, we follow. We first of all differentiate the function itself. So I have to take the derivative of this. So I forgot most years ago. I don't care anymore. So differentiate this crap. All right. All right. Good. All right. Now what we'll do is set equal to zero like so, and then solve for R. So let's see what the heck is this. This is 12b over R to the 13th. Over here. It's right here, 6a over R to the 7th. So cancel here. R to the 7th cancels out becoming 1 over here. 6th. So cancel this and make this a 2. Now solve for R. So when you solve for R, you end up with R to be equal to 2b over A. 1/6 power. Notice it's a little bigger than this number here, where the potential energy is zero across the axis. So now in parts A through D, I have all of the pieces here of the puzzle that I need to now go ahead and graph out the function that therefore looks like this. Good. Crazy. So we'll okay with that? Okay. Now, my function, I'll draw it nice and large. As then therefore, look like this. So, right here was A over B to the 1/6. The minima. Here, this is 2a, 6, and then we approach 0 all the way. Okay, I was at 2a to b, it was b 1/6, 1/6.
Would it be over
A,
A?
I'm sorry. Like so. So that's our potential energy function in red. And now, just very simply on the table, we describe what can happen in this column here, parts F and then G. Take a little amount and copy down parts F and G. motions here for my potential energy diagram. Let's actually start with a total energy E that's a negative number. So our total energy E being negative is then referred to a horizontal line. So, notice the atoms within the molecule are going to be confined. They're going to be confined to this potential well. Now, mathematically, what does this potential well look like? It looks like a parabola. And what potential energy function is parabolic? Spring potential energy. This is specifically why we can model covalent bonds just like springs. So if I somehow take this diatomic molecule and give it some energy by stretching it out and then let it go, all that happens is that the molecule oscillates like so. Each individual atom acts as a simple harmonic oscillator as long as the molecule doesn't give off electromagnetic radiation, which we are ignoring here in this context. So if I give the molecule some energy, it then oscillates like so, just like a mass attached to a spring. I have here essentially a parabola on my diagram. Okay, next, what happens if I give the energy of the object as a total amount equal to 0? So, what would happen then? Well, notice what does happen. For example, take the molecule and begin by compressing it. If I compress it, I would mention compress it to a point right here, that this specific value of R, or right there is potential energy in red is equal to its total energy E in blue. So what is its kinetic energy equal to right here? It's equal to 0. And then I let go of it, and what happens? Well, remember that at infinity, potential energy is equal to 0. So then therefore, what is the kinetic energy equal to at infinity? It's also equal to 0. What I've literally done is I've taken the molecule and I've broken it apart. I've broken the covalent bond. The energy necessary to do this is described here on this diagram. Mathematically, what it means is that the atoms end up infinitely far apart from each other and they end up at rest with the kinetic energy of 0. I've broken the molecule. It's the energy necessary to break apart a diatomic molecule. But if I give the molecule even more energy, I can say compress it even more, if you will. If I compress it even more beyond this point, then when I eventually break the molecule apart and the objects, the atoms, end up infinitely far apart from each other, then they will have some kinetic energy, which will be the difference between the total energy of E and the potential energy of red, which is equal to 0 when it's infinitely far away. So you break apart the molecule and the atoms then just keep moving at constant speeds. Notice that all of this can very quickly and very easily be described here, just qualitatively from the diagram itself. And then the last step in part G, we actually already did, because I already did the calculation in part D of the problem. I found the derivative. The force that occurs between the atoms is just the derivative that I calculated, but the negative value of that. Just make a note of that in your notes. Part G, that function that I took as the derivative, that function itself is the force that occurs between the atoms, where it has the negative sign at tip. And that force that occurs between the atoms is conserved in nature. Question, yeah.
So the middle, like the line is on 0, this is just the energy to break the bond.
Yeah, to break the bond. This is the minimum energy necessary to break the bond.
And then
Basically
the
what
line
it means is that I have to compress the atom to this point. If I compress it to that point, boom, I'll break the bond. If I compress it any further, then I give it so much energy that when I break it apart, the atoms are still moving after the bond has been broken. So something like this is what's happening in a chemical reaction when a diatomic molecule is broken. Both?
Kinetic energy when they're attached to vibration.
Yeah, it's vibration, that's right. So here in this potential energy well, at the endpoints here and here, whatever those values are equal to, the kinetic energy is equal to 0 at that instance. It's like the oscillator, for example, is at its what it's called amplitude positions, like so. And then it's like they're at their equilibrium positions, passing like so with kinetic energy right here at the bottom of the parabola. Okay, let's take a short break. Jay?
She told me she got it wrong in the test. I went in, she told me, but I don't know.
Variance is just, are you talking about the formula?
Oh, it's the square root of the, no, square of the
Last time I was doing that in the step before you have something like, when you're doing that's variance. So it just needs to be a square. So try that on your calculator, you know, square.
It represents an unallowed region.
In this calculator? Yeah, it's just, I mean, you would do it like that. To be honest, I think most people really down their calculator.
So basically,
We pull that back in this diagram, it's basically flip upside down as it goes forward. We deal with that just
You gotta work it out.
I don't know. So it can
I'll tell you when I was really broke. I'm not even supposed to be here.
So your spring can never end up with your house as long as I can't have I'm literally supposed to be back on this Thursday. But I don't play Griffin. I stood up, but I know. I feel I'll go like 30 minutes. If
But even if
I'm gonna go with parents. I'm gonna have some bonding time. Everyone else will be partying it up in their cars. Class no, it's not like I'm gonna waste my house. Halloween and the morning after.
then like, how late it gets there?
I don't have that. Like, I don't know.
Take your seats. Do not touch the toys. Put them back in the time.
What's up?
The last topic here for chapter 8 is very short and sweet. It's a brief look at power. You're introduced to it here in a mechanical sense. It becomes much more important later on eventually, however, when we do get into electric circuits. Okay, power is a defined quantity. We define it first as an average, and then as an instantaneous quantity. But first of all, qualitatively, power is equal to work divided by time. It's the rate at which work is done. It's the rate at which energy is used. Now it is a new quantity, so let's check the units. You only need to know metric SI units at this point. Therefore, let's just take a look at that. I will briefly mention our English units as well. But primarily we work, for the most part, in metric SI. Okay, work over time is joules per second. Joules per second, given its own name, it's called watt. It's named after a 19th century mechanical engineer. Okay, now a watt, if you talk about it in the context of, say, a 60-watt light bulb, what that literally means is that you need 60 joules of energy per second to operate the light bulb, as we said. Okay, now in English units, it's just foot-pounds per second. That's all. Yes, it's stupid. However, dating back to pre-industrial times, dating back to agriculture, even before the scientific revolution, people tried to describe what the subburden can do in terms of work, the rate at which that work is done. This is where the term horsepower comes from. One horsepower was originally described pre-scientific enlightenment, if you will, back in the agricultural times, is essentially the rate at which a horse can do work, whether it was on a farm or something like that. It now has a specific number attached to it. We've defined quantity. The quantity itself, 1 horsepower, is equal to 550 foot-pounds per second, which is the equivalent of 746 watts. You'll kind of see this number here in action, get a nice ballpark idea as to what it means in a simple problem, which is what minutes. Okay, now, as I said, we define power as the rate at which work is done or the rate at which energy is used, the same thing. But we do define it in terms of an average of an instantaneous quantity. The average quantity is defined in the following way. Average power, P bar, is equal to work done by the force, whatever it is that's operating, as we say, divided by the amount of time. So it's just total work done divided by total time, nothing more than that. But how do we reduce this to an instantaneous quantity? Well, we reduce it to an instantaneous quantity in the following way. Take a look at work. Work done by a force is equal to the following integral. What we will do, however, is think of it as the infinitesimal amount of work done in an infinitesimal amount of time. So I'll ditch the integral sign by thinking of it in the following way. So infinitesimal amount of work done is equal to that dot product. Therefore, instantaneous power P, which is equal to the infinitesimal amount of work done, divided by the infinitesimal amount of time, is equal to the following. Notice the right here, I have derivative of position with respect to time, which is a So then therefore, instantaneous power force times speed. But it's the dot product between the force vector, whatever it is that's applied to force, and the velocity of the object, the force is applied to. Now, all that we're going to have here is a basic introduction to these terms and how they're calculated for simple mechanical situations. We're not going to make this complicated at all. Let's just take a look at two basic examples. With the examples, it will become very obvious very quickly how this term works and what it means. Let's try something, first of all, just in terms of metric SI units. As we examine this problem, you're going to see why we run into a big problem very quickly when it actually comes to trying to do mechanical work quickly. In other words, you're going to start to see the limits of engineering in problems such as this. Now, notice the situation that's being described here is very simple. So you've got a machine of some sort. You've got a 1 kilogram object that the machine is going to do work on. You pull it horizontally across the surface. There's a little bit of friction. You do so with a force of only a couple of pounds, 10 newtons. But you do it not for a couple of seconds. Like this. Say you do it for 5 minutes. Then what we're going to calculate, first of all, in charts A and B, it's just a little bit of basic mathematics. Possible numbers, however you're going to get to. Do calculate parts A and B. And then after that, then we'll get to the power calculations. We'll do in part C, average power calculation. The machine is causing all of this friction. And then we'll also do an instantaneous calculation of the area. Watch the numbers come up with parts of this problem. Once again, small amount of force, a couple of pounds. Pulling the object, doesn't weigh all that much, doesn't ask to kilograms. The friction. You don't do it for a few seconds, you do it instead for 5 minutes. So watch what happens now. Parts are going to be, and we do a little bit of F equals MA. Okay, so as we pull the object to the right-hand side, we'll say on the diagram we have the following forces. The force of gravity, like the good old days of chapter 5, for example. The pulling force from the machine is equal to 10 newtons. And we have the force of the friction imposed on itself. So if we did a little bit of F equals MA, we have horizontally, pull minus the force of kinetic friction equals MA. And that's the object. So then, by the way, kilogram, and use it based on coefficient very small, it's 1. Okay, so just finishing the calculation here for the acceleration, friction is normal force, accel divided by the mass on both sides, acceleration, acceleration. It's not going to be all that much, it's a little less. So we have 10 newtons first, with 9.1 times 9.8, and it comes out to be, as I said, a little less than G, it's 9.1. So it literally looks something like that. But as I said, I don't pull on the object for a second or so, as I just did across the desk. Now we do it for 5 minutes. So then therefore, at this point, we just do a little bit of kinematics. In part A of the problem, I'm going to find the object's final speed when it starts at rest. That final speed, V, is just going to be the acceleration multiplied by time. Now the time is 5 minutes. How many seconds is it? It's 300 seconds. Watch this. So 300 seconds multiplied by 9.2 is the following. It's 2,706 meters per second. That's nearly 3 kilometers per second. Why can't I do that when I do this? Okay, now watch what happens in part B of the problem. part B of the problem, we calculated distance from x is doing a little bit of 1/2 squared. That's 1/2 times 9.2 times 300 squared. And that comes out to be, in terms of meters, 405,900 meters. That's about 406 kilometers. That's a couple of hundred miles. So if I started with this object at 1 kilogram on my desk, pulled it like so, at a force of just 10 newtons a few pounds for 5 minutes, I would end up out in the Mojave Desert, and the object would be moving at a speed of about 3 kilometers per second. Why can't I physically do that? For the following reasons. What we'll do is average calculations first, and then we'll finish up with an instantaneous calculation right at the end of the problem when the speed is 2,706 meters per second. So that's how we'll do part D of the problem right there at the end of the problem. So now what does the average power output, as we sometimes say, have to be associated with the machine in this problem? Now in part C of the problem, the average power output into the machine is going to equal the work done by the machine divided by time. Watch how big this number is. Now the work in this problem is just going to be force times distance. This is just a one-dimensional problem, so then therefore we're going to have here the F pole multiplied by x, and then we divide by time. So the F pole was 10 multiplied by the x of 405,900 meters, and then divide by the time of 300 seconds. And in terms of watts, we end up with a really big number. 13,530 watts. Now what does this number mean? This is the average rate at which you have to deliver energy to the object itself in order to accelerate it up to this speed. And travel this distance. The amount of energy per second you have to deliver to the object. You are constrained from doing this by two things. Number one is the energy density, as it's called, the fuel. In other words, how much bang for your buck do you have? You can only convert the chemical potential energy of your fuel into kinetic energy so quickly based upon the fuel itself, how much energy it contains per kilogram, for example. So that's your first constraint. And then the second constraint is the physical structure of the machine itself. In a physical way, how do you deliver the energy as chemical potential energy then directly to the object as we push it in this manner? From the physical construction of the machine itself, you're limited in how quickly you could transfer the energy, or in this case, transform the energy from chemical potential energy into kinetic energy. This is one of the big hurdles that we have to get over in engineering. How quickly you can move the energy from one form to another, in this case chemical potential energy, into kinetic energy. Now in addition to that problem, there's another problem, and it has to do with friction. So now what we're going to do is calculate the average power loss due to friction. This is how quickly you lose energy per second, and in what form does that energy take due to friction? It's heat. You have to dump, as we say, this heat. You have to get rid of it. Now, the average power loss due to friction is going to be the work done by friction divided by the time. Remember that the work done by friction in a horizontal case such as this is equal to the following formula. And we divide it by time. So coefficient times normal force times distance, like so. So what is this number here? Even if the coefficient is small, this is still a pretty big number. It's negative 0.1 times 9.8 times 405,600, or 9, and then divided by 300 seconds. This is still a pretty big number. This is about negative 1326 watts. As an average calculation, this is how much energy you generate as heat per second. You have to get rid of this energy, you have to dump it, as we say. This is what your radiator is for in your car engine. Because if you don't get rid of it, what's going to happen to your machine? It's either going to melt or it's gonna blow up or something like that. So you have to get rid of the heat that you generate as well. This is, by the way, why you always wanna make sure that you oil your engine. Because by oiling your engine, what you are doing is you are taking this number here and you're making it as small as you possibly can. You want that number to be as small as you possibly can, because you want this number here to be as small as you possibly can. So then therefore, always make sure that you oil your engine regularly. I've got currently, I think, 250,000 miles on a 15-year-old truck, and I still keep it going maybe for another 5 to 10 years. So I oil that sucker every 1,000 miles. And then lastly, D. The problem compounds itself. It compounds itself in the following way when you look at the instantaneous calculations. Now, the instantaneous power output due to the machine is just going to be force times speed for this particular problem. We'll specifically calculate this, however, at the end of the problem when the speed is 2,706 meters per second. Watch how gigantic this number is. We're only talking about a 1 kilogram object. So 10 times 2706 comes out to 27,060 watts. In order for me to keep pulling the object at this speed, this is the rate at which you have to convert chemical potential energy into kinetic energy. You have to change 27,060 joules of chemical potential energy into kinetic energy per second to keep this 1 kilogram object moving at a speed of nearly 3 kilometers per second. But then in terms of friction, the problem is compounded as well. The instantaneous power loss due to friction is going to be basically force times speed. In this case, frictional force vector is opposite of the motion, hence the negative sign. This number here is the following. Once again, this is why you want to oil your engine. So 0.1 times 1 times 9.8 times 2706. This comes out to be 2652. For each second, that's how much energy is generated per second due to friction with the ground. You've got to get rid of that heat. If you don't, you can suffer some sort of catastrophic engine failure, say goodbye to your truck. It's time to go buy it. So this is why we can't do things like this easily, because of these power calculations. That's why power as it's defined in this manner is so important when it comes to engineering. Now, at the beginning of this process, I mentioned horsepower. And we finished by just giving you a basic understanding of what that is. Those of you, by the way, that are into cars, a high-end sports car, how many horsepower is usually contained with the internal combustion engine? It's usually a couple of hundred horsepower.
How high are you going on Johnny's?
Yeah.
The newest.
Bugattis are not. Speaking of trouble with mechanical engineering, you guys saw that yesterday.
What happened? Wait, what happened?
That sucks.
What happened?
Oh, they're shooting a rocket.
Rocket blew up on the
No, it was just supposed to,
You know what happened?
It's Manchester great.
They know why. They don't The Chinese just actually got
A horse pulls a cart horizontally while exerting the force of 80 pounds. Notice immediately the English units. We're going to keep this simple. The horse pulls the cart at a constant speed of 10 miles per hour. Now, as long as we're at a constant speed, what this means is that the instantaneous power output of the horse is exactly the same as the average power output. What is the instantaneous power output of the horse? It's very easy to calculate. I'm just going to give you a taste of what is meant by horsepower and how it relates to these. Okay, 10 miles per hour, by the way, is a little bit above, of course, human walking speed. It's kind of like a light jog for a person, maybe a brisk walk for a horse. and it's pulling, in this case, a load of 80 pounds, which for a horse is not all that much. Okay, now, because it's pulling at a constant speed here, just horizontally, to make it simple, of 10 miles per hour in this case, as I said, this means that the instantaneous power output, the average is the same thing. So all that I have to do here is calculate the instantaneous, it's just force times speed, and that's good enough. So the instantaneous power output of the horse, is equal to the pulling force that the horse exerts multiplied by its speed. Once again, I'm just assuming here that the F pole is in the same direction as that of motion. To keep it easy, it's nothing. Now we do have to be in the right units. The force is in the correct units at 80 pounds, but we do have to take the speed here, V, 10 miles per hour, and convert that into feet per second. We'll then end up with a quantity in terms of foot-pounds per second. We'll then convert that into area and horsepower. So it's just a couple of conversions that we have to do. So we have pull is equal to pounds, the force is in pounds, units, and the speed V is 10 miles per hour. So just converting quickly, let's see, in 1 hour there's 3,600 seconds, and in 1 mile there's 5,280 feet. So in terms of feet per second, the speed V then of the horse is 10 divided by 3,600, multiplied by 80. That comes out to about 14 and change, about 14.67 feet per second. And then therefore, the instantaneous power output of the horse, E horse, is just going to be the F pull of 80 pounds multiplied by that. So it's easy to calculate. We end up with about 1173 foot-pounds per second. Now, you certainly don't need to know this off the top of your heads, but there's 550 foot-pounds per second per horsepower. So right after that, it's about 2. So you divide by 550, that comes out to be 2.1 horsepower. Like so. So you basically have a horse pulling a heavy cart at a light jog. The power output is about 2.1 horsepower. That's essentially what a horse can do. So take that number and multiply it by a few hundred. That's what high-end internal combustion engines can do, like you see, for example, in high-end sports cars. So we do, in fact, still use the term horsepower to describe the internal combustion engine, because when it was originally invented back in the 19th century, immediately everybody started comparing it to horses, just like they did with steam engines a little bit earlier in the mid-portion of that century. That's how it works. Because this is how it's defined. Okay, if you want to get an idea of 1 horsepower, it's basically that same problem, but instead of pulling at 10 miles per hour, you pull at 5 miles per hour. So it's basically the rate at which 1 horse could do if it's just pulling something like this at 5 miles per hour. That's the basic idea. Okay. So the term horsepower was originally defined in agriculture. We've now quantified it to represent it like this. Okay. Take a look here at the board. Next time in class, I did add one problem here to the problems that I am collecting by hand, just number 92. Numbers 92 and 99 are both pretty straightforward with respect to potential energy diagram. Don't forget about the web assignment due on Friday. Next exam is on Friday as well, covering chapters 7 and 8. Of course, the basic expressions will be provided for you. It's still somewhat up in the air, but it may not be here on Friday.
Thanks. No show? Awesome.
Oh, no, please don't. I might find that a lot. Yeah, we I mean, you guys come check them out now. It's Honestly, I bet the first Dude, but the thing is, my internet's down. I can't submit anything. Like literally, my laptop won't collect. No, but I've been honestly just
Rachel, Suki, here today. Rachel,
I felt myself falling that was the part where
they can run way more than
No, we're just gonna do problems on the book. You don't want to do it.
You would get in trouble for it. Maybe let people go to the
Why don't you get on the point?
and be like, oh, this is great, thank you.
Hey, what do you guys if the one's already all I know is that
Go right
I'm already ready. Like 3 holes or something to like 3. I don't like for this week. I just wish I didn't Yeah, but in order-wise, you have to. I need to go back. I need to go back to like learning like learning words by parts. I need to go back all the way to that. Everything. The thing is just like I don't know why access to the area of that area of that shading region.
No, I know. Look, I'm all I need to do is all my yeah, I'm gonna post it. I studied that. Find out what it is. It's gonna take me like 4 hours. Then I'm done. I want to know if it's hard. Then I'm done. What they're bad is I didn't do all of the stuff. That's the only so hard.
Intellectual vitality is the anatomy is yeah, that really wanted to I need you to help me like read them, right? Yeah. Now I'm amazing. Yeah.